Now we have learned something about proportion, how to calculate confidence intervals for proportion. And it's time to talk about the average, the next statistics, which is widely used. Most of the time you will calculate the confidence intervals either for the average or for the difference of average values, okay? So we have the same idea. We have population parameters, in this case mu and sigma, and we have sample statistics, M and S. And the point is that we don't know anything about population. Oh, probably we know that the values in the population are distributed normally or maybe not normally. Can we use the sample statistics to estimate the population parameter using these confidence intervals once again? Okay. So the intuition is similar. Let's take many samples of the same size from the same population. We will end up with many different average values, right? So for every sample, we will have slightly different average values. Sometimes it will be below the true average of population, sometimes it will be above. So it will vary around the true population value, okay? So if we know the distribution for the average values, and if we know how to compute parameters of this distribution using only one sample, like we did it with population, then we can do the same trick. So we can calculate interval based on these parameters, okay? So let me show you a couple of simulations. In this case, I created a population. It's a 50,000 random numbers, absolutely normally distributed. That's the average and that's the sigma. Let's think about height of people in a small city, or relatively small city. You can see that most of the time, the smallest value we've got 140, the largest was like 210. And most of the values are somewhere here, so between 160 and 185, okay? And you see that they are perfectly normally distributed. But this is a population. What I did, of course I simulated it, but you can assume that we did it in reality. So I took 200 samples of size 500. So it means that I went to the city and selected 500 random persons and measured their height. And then I repeated again. Every time there were some different persons randomly selected from the whole population. Then I calculated average value for each sample. So I ended up with 200 average values. Let's look at the distribution. So that's the distribution. This is you see that even though we have pretty big range for the values, the average values are distributed between 173.5 and 176.5. You see that they exactly are distributed around the true average. Okay. Of course, in this case, we took a lot of samples, and with one sample you cannot get that, but it's just an intuition. Okay. So the true 175, sometimes we got 176, sometimes we got 173, but most of the time it was somewhere around the true value, So it means that for this particular population, average values are distributed normally, and then the average of these average values, we have average values here, right? Average values of the sample is the same as the average of population. Okay. So if you calculate the average of all average values, we got 178.98, which is pretty close to 175, right? Now, look, let me show you this confidence intervals for this particular population. So this is the population, and this is the possible, it's a distribution of average values for my sample, okay? So here we have X, here we have values, here we have M, which are possible average values of the sample. And you can see that they are normally distributed. If we know the parameters of population, we can make a perfect normal distribution. So in a pretty narrow, because the sample size was large, in a pretty narrow interval, okay? And then we can calculate, for example, in this case, I calculated 95% interval, it's this one, which I just took plus minus 196 of standard deviation for the sample average values, not for the real values, okay? We will discuss this sigma m a little bit later, so let's concentrate on the visual illustration first. Now, if I do it for the 99% interval, that's 99%. So if you compare it back and forth, you can see that the 99 is slightly larger, so the uncertainty will be slightly larger, but at least we know that it's 99% cases that we have the average of sample within this interval, okay? Now let's discuss another population. I have the same population size, the same average, slightly different standard deviation, but you can see that the population now, this one, is not distributed normally. I have uniform distribution. What if we do the same trick? Or what if we take a lot of samples of the same size from this population? The funny thing is that they will also be normally distributed, okay? That's one of the major law in statistics. Average values of samples, so sampling distribution for average values, is normal, regardless how population is distributed. That's one of the things why normal distribution is important in statistics, okay? So it doesn't matter which distribution your population has. The average values for random samples taken from this population will be always normally distributed. And they will be distributed around the true average value, okay? So we have learned one thing, which distribution to use. So for average values, like for proportion, the distribution for the average values of your samples, sampling distribution for mean, for average, is normal. Now we need to learn only two things: how to estimate parameters of this distribution. I'll show you the same confidence interval. You can see that this is x, this is our values of population, different people with different height, and this is m. It's average. So if we take, for example, one sample with 500 persons and measure height of these persons and calculate average, this average value will be situated, in most of the time it will be situated in this interval. Then, look, if we know the parameters of the distribution, that's the distribution, we get rid of the smallest, the extremely large values, we get rid of extremely small values. So it means that 95% values of most common, of most expected values will be located here. And that's our confidence interval, okay? The problem is that to make this curve, we need to know the parameters of this distribution, and these parameters should be calculated only by using one sample only.